Welcome to Advanced Reverse Engineering. There's homework due on the 2nd of November. The homework is to do something that you've already done manually. So we had a finding main homework where you were required to find the address of main in a piece of code. You did that by finding the entry point, and then from the entry point you looked for how RDI was set, and that lets you know where main was. You're going to do exactly the same thing, except now you're going to write code that does it. So here's how it should go. I'll run your code, I'll give it an ELF program which has a main, and it will come back and tell me the offset to that main. Or I'll give your code something that doesn't have a main, and it should come back and say it cannot locate main. Use those characters in that order so that my code will recognize it. If you generate an error, output something that begins with the text error. Uppercase, lowercase, don't care. Use the error function that I've given you, or don't care. But if you put an error at the beginning of it, my checker will detect it and handle it correctly. So I'm going to give you an ELF binary executable. Your job is to locate the entry point and disassemble the basic block starting at that address. You should look for a call followed by a halt at the end of the block, and then from that point you should move backward. So if we're at address 100, you should move back to 99, but you should move backward through the instructions, and you should look for a prior instruction that sets the value of RDI, because RDI is going to be the first argument to the libc call main, and that's going to be the one we want to find. You want to find that value because that value is main. Once we find it, we'll compute that address. It will be either an RIP relative address, like an LEA, RDI, RIP plus some offset, or it will be an absolute address, move RDI, comma, some absolute address. Okay, look for both of those cases. Call your program main.py. Don't try to parse the text of the disassembly. Capstone provides all the stuff that you need. Really. If you find that you're trying to break apart the text that makes up the operand, don't do that, please. No, use the Capstone library. It's got lots of information in it. Just poke around with those things in IPython, and you'll do fine. Watch out for RIP relative addressing or absolute addressing, right? Look for LEA in main, where the target is RIP, and then you'll look to the value and you'll figure that out. Now, for figuring out the RIP relative addressing, be aware the address of the instruction you're looking at is not the address of RIP. RIP is the address of the next instruction. So you should add the length of the current instruction to the instruction's address to get the correct value for RIP, and then add the offset. Assume the instructions you want will be in the text section, and you should handle all the different cases gracefully. My suggestion is that you accumulate the block up into an array, and then you move backward from it, looking for the last LEA or move that sets RDI. You should also look for the call and the halt, because the call is going to be your tip-off that it's actually setting main. Lots of things assign to RDI. Just finding something that assigns a value to RDI is not good enough, because it doesn't guarantee that you're looking for this. This heuristic doesn't guarantee it either, but it gets you a lot closer. You'll want to turn on details. So when you make a CS instance, that's when you invoke the thing and you pass it x86 and 64-bit, those markers, and it makes a CS instance. On that instance, you want to set details to true. And watch out for prefixes in the mnemonic. And there's some Python code that will extract just the mnemonic. So prefixes obviously come before the mnemonic. This line breaks up the mnemonic text into white space separated words, and it takes the last one, which will be the actual mnemonic that you want. Let's talk about semantics. So it would be great if there were a beautiful, complete, usable, wonderful semantics for the x86 instruction set. The fact that I'm saying it would be great if there were should indicate to you that there's not. Now, it's not for lack of trying. There are some really good attempts out there, but no one has a really powerful full semantics for a couple of reasons. One of them being that what does it mean to be complete, right? In what sense is it complete? Does it tell me how these things align in terms of the microcode that gets executed? Does it tell me how many cycles an instruction takes? I mean, is all that spelled out? Are the cache implications of an instruction spelled out? Probably not. I don't necessarily need that level of detail for most of the things that I do. And usable? What does that mean? What does it mean to be usable? Usable for what purpose? Right? Maybe I want to do something really simple, like find main, in which case I don't need to have a deep semantics. Maybe I want to do something a little more complicated, like I want to find live variables. All I may need is written and read. Or maybe I want something even more sophisticated than that, and I need more details in my semantics. Semantics is a model. All models are wrong, but some models are useful, right? The only true model of the code is the code itself. What we are doing is constructing a model because that model we build is simpler in some meaningful way than the original code. Or it's something that a machine can process symbolically, whereas it can't necessarily process the original code symbolically. All right. Complete in what sense? Maybe we care about things like parallelism and timing. Those details can be meaningful and can make sense and be useful. But maybe we don't need all that. And maybe what we want is a partial semantics that's actually more useful. Including all these details can actually render it less useful. It can add a lot of complexity to it. And we'll see an example of what that might look like in just a bit. So maybe we need a simpler semantics that has less details. Just depends on what you're trying to do. And usable by whom? Is it going to be composable? If we're focusing on analysis, we'd like things to be composable. Like we'd like to be able to break a program up into chunks and then analyze the individual chunks because they're small and analyzable, and then be able to compose the results back together. And that's a nice property of functions and relations, and so maybe we'd like to focus on that for our semantics. Maybe we'd like to run the code. Maybe we'd like to have an operational semantics that I can actually execute, maybe symbolically. Maybe I say, the input value is X, and I execute the program symbolically to see what the result is. That's fine, and there are ways to do that. Maybe I want both. Maybe I can represent the semantics in Lisp or ML. If you're not familiar with Lisp, Lisp is a functional programming language. So is ML. Both of those are really powerful languages in different ways. Lisp implements a lambda calculus. ML does as well, but a different sort. And I can represent the semantics in those, and that may have the advantage that I can also execute those forms and see what happens. Is the primary consumer a computer? If so, maybe the syntax needs to be easily parsable. Is it a human? Maybe it needs to be more forgiving, right? How important are human factors to all this? Let's talk about representations of semantics. One representation, one I'm very familiar with because we used it in a piece of code we built, is the conditional concurrent assignment. And over here on the right, you see an example of it. So add with carry EX and 17. What's the semantics of that? Well, we have one condition and it's true, so it's always this. Well, we say we have a whole bunch of things over here on the right side of the equal and some things on the left side. And the idea is there's state. The machine has state. And we represent the new state over here on the left in terms of the old state over here on the right. And everything happens in one smash. we compute each one of these by plugging in the current values. And once we have all of these computed, then we assign. So I don't assign to EAX and then ZF and then SF. I assign them all at the same time. Concurrent assignment. So that means that EAX plus 17 appears several times in here because I need to reference it several times. If you don't want to do that, maybe what you want is a sequential assignment where I would then do this EX plus 17 and then I could go on to these next ones. The problem with that is it means the order of them is important and significant, and it can then become tricky for me to omit some. Right now, what I have over here is both associative and commutative. The order I do these doesn't matter, and so that can be very powerful. But if you like the idea of sequential, maybe the binary analysis platform is what you want. Let me go back. This approach is used in Hyperion. I believe Hyperion is now called Code Hunter. There's a link to the company. It's a tool used to analyze malware. Conditional sequential assignments are used in the binary analysis platform. That is a piece of code that won the DARPA Grand Challenge. So David Brumley's team, smart guy, was at CMU at the same time I was, and we had a lot of discussions, and I think he didn't particularly care for our concurrent assignment, so he went with sequential assignments. And here's an example, and you can see a few differences immediately. There's the AT&T syntax looking at you, and here you see I've got a temporary because I'm going to increment. I'm going to add 1 to RAX, so there's RX gets RX plus 1. But occasionally he needs to refer to the original value of RAX, so he has to then save it up in a temporary and then be able to refer to it down here whenever he needs to. Different kind of approach. Maybe you like Lisp. Here's some Lisp representing a whole family of these instructions. And so it's a different kind of slice through the semantics. Instead of giving an instruction in full detail, it gives full details on parts of instructions. This is from the x86 ISA book for ACL2, right? Once you're in the functional programming world, you can't use regular names. You have to reuse names in ways that are strange. And so instead of being a library, it's a book. And this then gives ACL2 the ability to do some analysis. ACL2 is interesting because it was used to prove the correctness of the division algorithm in the Pentium after it was found to be problematic. K expressions. K expressions. If you thought Lisp was verbose, here's the K expression for this, and you can see it's significant. It's got a lot of stuff going on in here. And before you laugh it off and think this is crazy, this is not meant for you to read and look at and consume. This is intended to be used by the computer to do some computation for you. And the K stuff is really powerful. It captures a lot of the details of the semantics. It can execute stuff. It's been very heavily tested. It's a much more complete semantics than most of the others, and much more heavily tested. Maybe you want your semantics to be something that you can compile as part of another program. This is part of the semantics used by the ROSE compiler. ROSE is a source-to-source compiler. So instead of compiling your source code to machine code, it compiles your source code in one language to source code in a different language, which is a really neat thing to do. It's really hard to build. If you're curious about it, you can go on to Docker. I've got a Docker image that I put up there where I built ROSE. So Dan Quinlan's team out at Lawrence Livermore builds and maintains this, and it's a really neat, very powerful tool. It's gotten a lot better in terms of being able to work with machine code and with assembly. Since I introduced Dan to Corey, and the two of them have, Corey's been beating on and breaking ROSE, and Dan's been fixing it. It's been a really good relationship. Those are all different forms, right? And there are many others. There are often things for theorem provers, etc. For example, over on the right, you see x86 construction semantics and basic block symbolic execution. That's done for the Isabelle theorem prover. And if you dig into that little abstract, you'll see it provides semantics for roughly 120 different assembly instructions. And you already know there's a huge number of those, more than 120. So this is an incomplete semantics. But it's useful for certain purposes. Even the most complete and tested semantics frameworks will omit or hand wave certain things. In the case of the K stuff, super heavily tested, thousands of programs, but it still omits the concurrency stuff. If you'd like to know if that's important and what you might be able to do with it, there's a link over there that shows you some of the things you can do if you have a model of the x86 concurrency, and it can really pay off. Those models that you'll see over in the links on the right, they don't have all the other stuff, right? They just really focus on concurrency. So again, it's the semantics modulo what it is that you need to do. Let's pick on one particular one. Here's the conditional concurrent assignment. In this case, it's for ADC. I could plug in values for op1 and op2, substitute them into the body, and that would result in something that told me what was going on. Here is increment. Looks very similar. Let's put increment and add side by side. So on the left-hand side, we have add 1 to EAX. On the right-hand side, we have increment EAX. And they should be the same, right? We're adding 1 in both cases. What's that? There's something going on here. In this case, we set the carry when we add, but we don't set the carry when we increment. That can be important. Why would that be important? Well, let's say I'm a malware author, and I would like to know if my code is being emulated. OllyDebug and some other emulators that were once very common got this wrong. And so I could set up a register, I could increment that register, and then I could check to see if the carry was set. And if it was set, I was being emulated because they'd gotten the effect of the increment wrong. And if it was clear, then I wasn't being emulated, and I can go on and do other stuff. So again, how complete and for what purpose? Maybe it's fine for me to say, increment just adds 1, increment's the same as adding 1. But if I'm concerned about things like malware, maybe that's not good enough, and I need to think a little harder. All right. Let's talk about a particular brand of semantics called P-code. So P-code is part of Ghidra. So you may be familiar with Ghidra. Let me see if I've got it open. I think I do. There we are. There's Ghidra. So here's Ghidra. I've got it open with a tiny little file. So you can see there's a load effective address with message. Then I call something, and I do an XOR, move, syscall, and halt. Pretty simple little hello world program. There's even my little data, hello world. Now, if I want to see the P code for all this, I go up here to the little Jenga button and click it, and I see all these different things you can enable or disable, and you might think, oh, there's P code right there. I'll click it, and nothing happens. That's because you need to right click it, and you need to enable the field. Now I've enabled the P code field. I can close up the little Jenga menu, and I'm getting P code. So here's the LEA, and you see right here, this guy is the P code for that instruction. There's a call, there's an XOR. See lots of stuff going on for the XOR because we're setting EDI, RDI, carry, overflow sign, and 0, some temporaries, and parity. Lots going on there. So, and you can sort of see how all this goes. So here's an example listing with the Ghidra P code copied into it. And let's take a look at it. In particular, let's look at this first one here. Because it's Halloween, and I picked the one that had the little scary in it. So you'll see this is in int scary. If you want to see the reference, it's linked over here. So there we go. P code is not huge and complicated. It's actually very, very simple. But it looks a little odd, and so it needs a little explanation. So there's int scary. And here's what it means. Here's some of the documentation. It requires 2 arguments. Input 0, which is the first var node, and input 1, which is the second var node. And what are these? Well, they're RAX and 1. And this is a 1:8. What is int scary? What's going on here? Well, the operation checks for signed addition, so the S is for signed, or carry conditions, and there's carry. So scary is really signed carry when these 2 things are being added. If the result of adding input 0 and input 1 as signed integers overflows the size of the var nodes, the output is assigned true. There you go. So in fact, you can see I'm doing an int scary of Rx and 1 and assign the result to the overflow flag. Should make sense. There are the arguments for it. Here's an example of setting the 0 flag. Right? What I do is I check to see if RAX is equal to 0. In this case, 0:8. Why is it 0:8? The :8 in these cases specifies the number of bytes in the constant. So this is an 8-byte 1, and this is an 8-byte 0. And that makes sense because these are 64-bit or 8-byte long registers. Set the 0 flag this way. You'll notice that there's some sequentiality here, right? So I look for the overflow flag here. Then I add 1 to RAX. And then here I assume, right, for the 0 flag, I assume that the RAX here is the result of this addition. So it's a little tricky. This RAX up here and this RAX down here represent different values at different points in the program execution. I could convert them into static single assignment, and then I wouldn't have that problem. But right now, they represent different things. There's some sequentiality in these. Ghidra is not perfect, nor is its semantics complete in a way we would like it to be. But it works well for what Ghidra needs it to do. So for example, XOR EDI, that sets EDI to 0. Done. That's all I need to know, right? Well, there's a whole bunch of other stuff. Ghidra provides all kinds of details here. The flags, all this stuff. These $sign things, those are temporary variables, so we can refer to them later, right? So it defines this one, refers to it here, to define this one, refers to that one here, to define this one, to then use it here. Other times, not so much. So here we have a notion of, we have an example of kicking the can down the road. What is the semantics of syscall? It's syscall. I don't know what it is. I don't want to think about it anymore. Stop. Leave me alone. So there you go. So now we have a notion of semantics, and we've talked about program slicing. Let's combine the two, and let's talk about semantic slicing. This is the program we've been slicing. And sometimes it's useful to have a snippet that can be compilable. And what can we add to this to make it compilable? Well, we can stub out the end, right? So we have the usual termination stuff. And we can stub out opt-C. We don't know what it is and what it does, but I'll just put a stub in here for it. Or I could make it an extern and then just a symbol. But if I want a link as well, I need an opt-C, and this gives me one. Great. We'll add a start label up here at the top, put global start, and then finally we'll put a make line at the top. We're ready to build the whole thing. Now at this point we can build it, we can run it in GDB, do all kinds of analysis with it. Or go back to the original program. Let's generate the P code for this using Ghidra. And when we do that, we wind up with this. So inc.rax has this P code, LEA push, so on down the line. One thing to take a look at here is the call _opt-C. And so we have a semantics for it here. All right, let's highlight that. Is this semantics correct? Well, yes. Everything in there is true, but it's also wrong. How can that be? What do I mean? Well, what do the semantics say? Well, the first thing they say is I subtract 8 from the stack pointer. And that's true, right? I'm doing a call, so I'm going to push something on the stack. The way that works is you subtract from RSP, and then you move the bytes you want to put on the stack into that space. So I subtract 8 from RSP, and then I store the next address into RAM pointed to by RSP. Correct. And then I do the call. And wait a minute. If I just blindly walk through the semantics, I wind up with the stack wrong. So unless I'm assuming the call is going to fix the stack through its return, is it? So the point being that if I naively execute this sequence of lines of the P code and just walk through it, I may get the wrong answer unless I go into this call down here and do it as well. I can get the wrong answer. So we're going to solve that using the engineering trick of omitting it. So it's going to omit it, not worry about it, and we're going to deal with the rest of what's there. So to do the slicing of this, we need a slicing criteria. And the slicing criteria we're going to use is what is the value of RAX at the end of this piece of code, right? What's the value of RAX immediately after this pop RAX? So to get there, we're going to use a little table. So the value of RAX, what we care about here, this column will hold the set of things we care about. We care about RAX, and we ask, is it assigned by this line? And the answer is no. RSP is assigned. So this line is not important. We can discard it. We then move, and this set doesn't change. We move up here. We ask, is anything in our set by this line? And in fact, RAX is in our set, and it's set. So that means we have to keep the line. RAX is on the left, so we throw it away. We replace it with RAM RSP because that's what we're using to set the value, and that becomes the thing we care about. We work back the same way with that. We keep the next line because it sets RSP. We discard some lines, keep some lines, until finally we work up to the last one, and there we go. Now, we only need the highlighted lines. Those are the ones we've chosen to keep. The rest we're discarding. And so let's discard them. And there we go. This is our sliced semantics for that piece of code. And it's pretty short. We have a temporary variable. 80 gets set to this and then used here and then not mentioned anywhere else. 00 gets set here, mentioned here, and not used anywhere else. So it would make sense to just say copy RCX and just plug that in here, and say intmul REX and 8 and just plug that in here. Let's do that. There we go. Even simpler. And we can proceed in a number of ways, but let's put it in static single assignment form. So we'll assume everything starts at 0, and so this is now 1. So REX of 1 is int add of REX 0 and 1, and we go on to the other ones. I can then back substitute over here, right? REX2 is load RAM RSP sub 2. I work through this and I find out that finally REX is the int mul of the int add of REX and 1 and 8. I can write it like this, or I can write it in assembly like this. So I can replace all that original code with this LEA REX and then the value of REX times 8 plus 8. There you go. That's how this works. we sliced on semantics, and that let us figure out something interesting about the program. Let's go back and think about liveness and slicing as they work in assembly. Well, we don't have a super convenient semantics to do this with, and the question is, how far can we get? And here's a naive algorithm to do slicing for us. My slicing criteria is the value of the variable v at location n. So I initialize my dependency set, the things I care about, to be just the set v at location n. Then I run backwards from location n back up to the top, or to the earliest lines. I get the variables in the depend set that are L values, that are things that are written, and I remove those from the depends set. So here's what I do. I figure out the ones that are written. I intersect that with the dependency set, so the ones that I care about that are written go in W. I subtract those from the dependency set to get the new dependency set. Then down below, if W was not null, I add the ones that are read back to the dependency set. Let me put some of the ones I discarded back in that set. If it is null, I can discard the line. And that's my algorithm. And I just walk backwards doing that. Let's apply the algorithm to this piece of code. We want to answer the question, where does this jump R11 go? So here we go. We put this in a trace table in this case. And you can see our dependency set over here. And I've kept track of what's written and what's read in these two columns. So I care about R11. And looking over here, R11 is read, but it's not written. So there you go. I don't care. Here, I play the same game. I check, and R11 is not written at line 6, so I'm going to turn out to discard it. And you can see the details worked over here. I keep walking back. Finally, I encounter a place where I'm going to keep a line. I work my way back, and there we go. I throw everything else away. This is my new sliced piece of assembly using just the read and write information. So after slicing, we're left with just 3 lines that set the value of R11 prior to the call, and in fact I can combine those, and really all that's happening to R11 is I'm moving this value into it. So I can replace that with a much simpler program as well. That's it. Take care.